So, hello and welcome back to Advanced Image Synthesis and Terrain Rendering. The last time we stopped around here, so we actually I got a few slides further, but let me first start from this point. I started with a few general ideas about terrains. Why should we consider terrains? Why are they important? Why do they deserve special treatment? Next thing, we looked at what could we do if we want to trivially render terrains, right? We take just the height field, for instance, turn it into a bunch of triangles, a lot of triangles, and render those. Or we could be a little bit smarter and try to generate a triangulation that is adaptive in two senses. First, in the sense of wherever the terrain is flat, we need fewer geometry, fewer triangles. Or where the terrain is far away, we can also reduce the number of triangles. So this is called static and dynamic LOD. So static LOD is reducing the level of detail, the precision, the number of triangles, the number of primitives, wherever the terrain is flat. And dynamic level of detail is the same idea, but depending on the screen size. And then I mentioned that there's a ton of different approaches, and that after a long sequence of research works, people figured out that these days, meaning where we have very fast graphics cards, dynamic remeshing, recreating a mesh so that it's optimal in the sense that it's as few as possible triangles with as good as possible placement for the vertices, is so expensive that just doing more work in the end ends up being faster. And that led to, yet again, a couple of works that try to work around this idea that, well, it's not a good idea to do nothing, to work with these gigantic data set, but it's not such a good idea to be like super optimal in a sense that we spend a lot of time trying to reduce the geometry. And there's a number of methods that kind of try to find a path in between. And I just want to look at two of those because they're specific candidates for types of approaches. So the first one is called geometry clip maps. And well, it's based on a very old idea actually called a clip map that was part of the very early OpenGL specifications already. And the second idea is what's called simply GPU-friendly terrain rendering, which is a method that is specifically tailored for the ways GPUs work. The clip maps are also tailored for GPUs, but they are based on, or geometry clip maps, let's just start with those, are based on this idea of clip maps without the geometry. Notice that geometry clip maps builds on top of clip maps. Now, what's the clip map? Clip map, again, is an idea that is kind of a relic from the time where there was extremely little memory, where you literally were working with kilobytes of memory rather than megabytes or gigabytes or terabytes. So when you have very, very little memory available, it makes a lot of sense to try to save memory wherever possible. And when the first GPUs were introduced, and those were mainframe systems, not things that you would stick in a commodity PC, they still had very little memory, but the users wanted to use textures, and they wanted to use comparably large textures, like, I don't know, 1,000 by 1,000 pixel or 10,000 by 10,000 pixels texture when you only have a few kilobytes of memory. And the basic idea was that you create this hierarchy of textures. That sounds familiar, right? So you have a full resolution version of your texture, which is large, way too large to fit into memory. You create a lower resolution version, say reduced by a factor of 2 in each dimension, so it's a quarter of the original size, and you continue this process up to the coarsest level, where you maybe only have 4 or only 1 texel. Okay, so that's the first thing that you build, and it's generally called a MIP map. Now that gives you different quality levels, but it increases the memory footprint, right? That doesn't decrease the memory, it's more, right? I mean, having this pyramid of things is obviously more than just one level. It's not significantly more, it's not like 10 times more or so. It's actually not that much more on that in computer graphics, but it is some memory overhead, and that's all we need to know here. So how does that help you to deal with textures when you're actually blowing up the memory requirements? Well, the basic idea of clip maps, again, all of this not considering geometry for a second, and we'll see that this can be extended to geometry as well. So what was the idea for clip maps? Well, the idea was that we texture the object that we're interested in a way that we consider only a part of the original texture, say this area here in the center. Okay, so I now projected a beam onto some place in the texture, so this place here, and this is selected, so this is close to the position of the viewer. Okay, so the camera position. Now notice that I didn't just pick, I don't know, 8 by 8 values or so. I created this kind of cone this kind of brick here through all of the levels, and that's very important because what I do is in a clip map, I read from the bottom here. So I read a bunch of pixels here from the bottom, and then I store in a map. So this is this center part here. And then I read another set of pixels, but in this level here. Okay, so I read a ring of pixels in this level here, maybe just one pixel wide ring, and that's stored around this. Then I read a 1 pixel wide ring here, and then I read a 1 pixel wide ring here. Now, since the extent of these pixels here, when I would project them back into the original map, increases, right? I mean, every pixel here stands for 4 pixels in the bottom map, and then every pixel here is 4 pixel here, 4 pixel here. Okay, so and so on and so forth. So this obviously means that every pixel here covers a larger area. Then, with just this this cross section here, I can cover a very large region. Up to this point where I cover in the coarsest level, actually this ring will just cover the entire domain. Okay, so that's first of all the idea of a clip map, and that can be used to then texture an object. When the camera is located here, I can texture an object with this set of pixels, and that can be limited. Depending on how wide I make my window here, I can limit the amount of data to whatever I have available on the hardware, but I can still cover the entire domain with just varying quality levels. Now, what happens if I move the camera? And that's kind of an interesting thing with these clip maps. If I move the camera in a somewhat consistent way, right? I'm not completely jumping around. Let's say I just move my camera, or I move the data set in some way. Then I can just move the center, and this means I need to just remove a ring. Notice that this is in every level. I just, well, in the courses nothing happens, but in the other level, I just remove a seam around my data, and I have to add a new seam. So I only add very few values. I just have to do some clever addressing, right? Because I would have to shift all the data if I don't want to shift the data around, but just override these positions here with those data. I have to be clever about the addressing of memory, but this can all be implemented so that basically a motion that is not very discontinuous, right? Just a smooth, continuous motion introduces a smooth, continuous, and very limited flow of data. Okay? And that's the basic idea of a clip map, that we have a multi-resolution representation of the data, and we have this the working set limited to a arbitrarily chosen amount of memory, the amount of memory that I want to spend for that particular purpose, and that also the data flow in and out that I need to update this this structure is also very low, is constant and very low, as long as I don't jump around. If I have a discontinuity in my scene and I need to jump from one point to another, I have to potentially replace the entire data set, but still, it's not a lot of data. I mean, that's the whole point. This will probably take a while, even if I only use kilobytes. If you think about an old machine, then transferring kilobytes from, I don't know, a tape drive or whatever, probably takes a while, but nonetheless, it's a significant reduction. Now, that's a clip map for textures. And geometry clip maps is basically exactly the same thing, with a few kind of tricks on top of that. So the first one is, for a geometry clip map, we use height field data here. So we don't use images or pictures or whatever you often use for textures. But we use a height map. We create this clip map structure. We get this coverage here. And then what you can see here is the triangulation that is computed from that one. So we compute a regular triangulation independent of the static properties. So that's an interesting effect of this technique. So it doesn't take advantage of the static properties. So flat regions will still be triangulated the same as curved regions. So that's a disadvantage, but it's a property. But it requires very little memory, just constant memory movement. And since the data is extremely regular, right? Notice that all of the data that is used here to create that triangulation, which can be done in a geometry shader, so that doesn't have to be transferred. Only all that's transferred is this data here. That is extremely regular. The triangulation is very regular. That means simple code. And that also means that we have a very simple access pattern. And that was one interesting idea that was used on top of the normal clip maps, for the geometry clip maps. And that's the colleagues that invented this idea were compressing or compressed the data. Okay, how did they compress the data? So their argument was that these pieces of data are usually across levels and from region to region are related. So when you have one height field value, another height field value, another height field value, there's usually some relation, right? They don't jump arbitrarily around. If they would do this, we would have something that probably doesn't look like a height field. We'll see in the next topic about terrain synthesis, we will actually see that most terrains exhibit certain properties and that we have limits on frequencies for terrains. So and their idea was, well, if we have this very smooth signal where there's a lot of correlation between points, we can use certain well-known lossy compression techniques. And they happened to work at Microsoft at that time, and Microsoft happened to develop a lot of video codecs. So what they would do, they would simply take the terrain and would chop that into pieces and take all those pieces as frames of a video, and then would simply run a video codec on that one. So the entire terrain effectively became a video. And when they wanted to access a certain part of the terrain to fill the clip map with that terrain, they would simply forward to that frame in the video, grab the image from that frame, and then copy it into memory. Since video decoding is accelerated by hardware, and it's a pretty well-studied problem, they were able to compress gigantic amounts of terrain data into relatively small sizes and handle those very efficiently. So that's really a fancy idea to run a video codec to crunch terrain data together. So, and it worked pretty well. So here you can see at the top right, you see a rendering of a terrain using these geometry clip maps. And if you just search your favorite engine, search engine for geometry clip maps, you can also find a bunch of videos that the authors published. And I think the code is also available for geometry clip maps. So on the positive side is the data has a very regular structure. It's relatively simple to implement since it's so regular. Due to the nature of clip maps, due to this sort of motion, this assumption at least that we have this smooth motion and then these smooth access patterns that we have, right? Always only the seams, they need to be accessed. This idea of a blockwise compression into video frames work pretty well. There's on the other hand a bunch of drawbacks of this method. One is that there's really no control for error. So we don't have a clue what the video compression does to the terrain. Okay, I mean, it's optimized for videos. It's not optimized for preserving terrain features, right? So while the results look okay, there's no guarantee whatsoever that something is preserved or not. And that can or cannot be an issue. What's certainly true is that a ton of triangles are usually rendered too much because we don't do any static simplification. We end up having the same high or low resolution for any type of terrain, whether it's flat or whether it's rough. However, notice that this is actually, it's a drawback. In this case, it's probably a significant drawback because we render a lot of triangles too much. But remember that my initial point was, well, rendering too much triangles, it's kind of the insight, a key insight that rendering too many triangles isn't such a big deal. Because as long as we do the rest of the pipeline very fast, we can actually afford to render a number of triangles too much. Another issue is, well, it's not adaptive, so that is kind of a similar. It kind of goes in the same direction of the number of triangles, and in general, it produces a relatively high pixel error. So, in particular, one thing, if you really want to watch geometry clip map video, which I think is probably a good idea to do, sort of as a refresher, when you watch those videos, I ask you to look at the horizon. Okay, I mean, they look pretty impressive, but take a look at the horizon in all of these videos. What you will see is that the horizon is generally flat. It's a straight line. Why? Because, well, at the horizon, we are always at those low levels, and since there's no control whatsoever over the error, we'll end up basically compressing everything to a constant. And that is probably not what you want. Without me saying this, is this obvious? It turns out it's actually not that obvious. So it's a flaw of the method, but it still works pretty well. For, let's say, gaming purposes, this is a good idea. For other visualization purposes, it's probably not a very well-suited technique. Okay, so those are the geometry clip maps. Now let's look at the second technique, this GPU-friendly terrain rendering. Okay, it's obviously something that is done well for GPU-based terrain rendering. And it's based on a number of ideas that are all combined into one big technique. So the first one is that it uses tile-based restricted quad trees. That is a similar thing than we've seen before for ROAM, this real-time adaptive meshing. I'll review a few of the things. But it's based on these restricted quad trees that can also be statically built, or that are statically built. So in regions with fewer objects, we end up with fewer triangles. So it allows for static simplification as well as dynamic simplification. It also considers the texture that will be mapped onto the terrain. Like in many scenarios, you don't just have the terrain, but you have a texture that comes with the terrain. So it also looked at concepts how to deal with that one. And one of the major advantages of this method is that it has a precise error control. So you can guarantee, for instance, that the error is smaller than 1 pixel on your screen, which is generally pretty decent, assuming that it's very hard to spot a subpixel error. Okay, so that's a real big advantage of that method here, that you can actually, even though it's from an engineering point of view way more complicated, it gives you way better quality at comparable speed. It's a little bit slower. It's about half of the speed as the geometry clip maps, but it gives you significantly better control over the quality. And you can make it faster if you increase the pixel error, of course. So what's the idea? The idea is, again, we start with the data, and in this case we start with a height field and texture. Those that also attend scientific visualization, you've seen that image before. It's the same idea that I introduced in scientific visualization. That's this creation of tiles, so breaking the data up into smaller chunks, and then creating this map, this MIP map of different quality levels. Okay, so that's kind of the same as we've seen before with the clip maps. We also had different levels. The key idea here is that we first chunk the data. So we first create these small tiles here, and then we only work on those tiles, which is very nice if you think about this terrain of being very big. So when the terrain is an exabyte in size, then just looping, I mean, open file load into memory is not going to work. Okay, but if you first chunk this up into smaller parts, then you can say, for instance, for this reduction process, we'll load 4 chunks. Each one is maybe a megabyte in size. Load 4 chunks. You can keep them all in main memory, compute the average over every 4 pixels of each chunk, store it into one other chunk, dump this into disk, erase the memory, load another 4. So that's the basic idea, that we start with this subdivision process and then do the hierarchy. Okay, So this leads to a hierarchy that can be visualized like this, right? So every 4 points are reduced into 1, and so on and so forth. Okay, and in the following, we will consider all of those partitions separately. So in the rendering system, it always traverses the data partition by partition. Okay? One partition shall not influence another one and shall not need another one. This is very important for this out-of-core idea. So this idea that the data is too big to be handled in core, in memory. So we load one thing, do something with it, delete it from memory, load the next thing, do something with it, delete it from memory, and so on and so forth. Okay, so one big thing is that we want to be able to render the entire scene while technically only being required to load one single chunk of data. So if one of these things is 1 megabyte in size, you can render an exabyte of data with just 1 megabyte of memory plus maybe the other memory that your operating system needs. Okay, so it's very well controllable. Of course, if you have a gigabyte, you can load 1,000 of these chunks simultaneously and process them. But the key inside is they should all work independently. If you do this independent thing, you run into one issue, and that is, let's just look at this example here. So this is one chunk being rendered, and that's another chunk being rendered. And they might be at different resolution levels. So say this one here is at a somewhat higher resolution level than this one here. Since we don't want them to influence each other, we can't, for the yellow one, we can't do anything to adjust it to the blue one. Okay, and that will always lead to a transition from one level to another can always lead to what we call T-vertices. Okay, so this is what you can see here. That's a T-vertex, right? It's a vertex that is T-shaped. And that is generally an issue. Why? And that you can see here, because the higher resolution version will most likely have a different shape than the lower resolution linearly interpolated version of that edge here, which you can see here, right? So there's a dent here. What happens is that this creates a hole, right? So if I would fill this part of the terrain and this part of the terrain with a texture, I could look through. So I see this small triangular shaped area here that I could see through, and that would create a hole. So I would see the background, which is maybe white or black or whatever color the background is. So I would see this, and even though those might be small, those holes, I would still get speckles or glittering or some sort of artifact on my terrain. To avoid this, the method introduces something that's called a seam. So notice these triangles here at the bottom. So every tile has some triangles that technically should never be visible because they all go straight down, and they are supposed to cover any of these seams up. And they have the same color, the same texture as the adjacent triangles. Okay, so that's, in a sense, it's a little bit of a hack to kind of cover up these cracks. They should be pretty small, so the cracks are generally smaller or in the order of a pixel, but nonetheless, pixels, single pixels that start to flicker are very disturbing. So this here effectively fixes it. Okay, so when does this happen? Well, it happens every time you have a transition from one level to another. Now, what does this mean, having transition from one level to another? How are these levels structured? How do I even come up with this blue or cyan triangulation here and with this yellow triangulation? Well, let's look at this idea of a restricted quad tree again. What was that again? Well, the idea was that we have our entire terrain. It's given on a regular grid, and we start with this high resolution version of a tile. Again, the system always works on a tile. So we work with, say, 512 by 512 pixels. We look at all of those pixels and we can turn them into a triangulation, right? We can just, every 4 pixels, create 2 triangles. And then we get a very regular triangulation. Now we check this triangulation. Is there maybe a pixel in that triangulation that can also be inferred from its adjacent pixels by just linear interpolation? Okay, meaning if I remove that pixel and create a larger triangle. So for instance here, you can see that this quadrilateral here is made up of 4 triangles, but this is only 2. Okay, so can I maybe just remove the vertex in the center here, reduce the number of triangles, and still retain about the same shape? And there's different ways how to compute this about the same shape. For instance, I can compute the area the sum of the triangles, right? If it's flat, the area should be the same. I could compute the distance to ground. I can compute the angles within the triangle. So there's various different ways, there's different metrics, but in the end, they all amount to the same idea. How different would the triangulation be if I remove a vortex? Okay, in this process, that's the pre-process that is executed on those tiles, figuring out which vertices can be removed. Now, I don't remove the vertices in an arbitrary fashion. I enforce some rules on that one, and that's what the restricted quadri idea was. So I make sure that within a tile, I only have transition from one level to the next level. What does level mean? Well, it means when I start with these, when I consider my data to be made up of little quadrilaterals that are each triangulated. I don't want more than a 1 to 4 quadrilateral shift from one quadrilateral to another. So one quadrilateral to adjacent quadrilateral should only be one level different. Okay, so and here you can see what happens if I have a transition that is higher than that. Say that's my original triangulation here, that's fine. And now I decide, okay, well, I need that one point at the top left. Okay, so I need one more point, or I don't want to remove this point. In that case, well, we'll put it there, but that will introduce a bunch of other points, as you can see, because it will introduce a t-vertex, right? So at, can I extend my arm? No, too short. Okay, so at the very top left, right, so if on this edge t, I add this additional vertex, that would create, would turn that one triangle into two, and on the other side, I also create two additional triangles, but to be able to create those, I first need to split that, and need to propagate this split. Okay, so this still allows me to use different resolutions, right? Notice in this fixed version here, this is still lower resolution than the one on the top and the one on the left, but it's only a level difference of 1 that I allow, right? So this one only is adjacent to a level difference of 1 to a quarter-sized triangle, okay? And this effectively avoids t-vertices within one tile so that I don't have to worry about cracks within the tile. Okay, so and this is created up front, and basically we use the same approach as Rome for this method here. So we have this dynamic, this static mesh, and this is what such a mesh would look like. Okay, so here I've drawn the edges very thick, so you can easily see them, and it's still overlaid by the by texture. And you see that certain areas have relatively low resolution, and some areas, well, around that black ridge there we apparently need more geometry to capture the shape. Now, one of the fancy ideas about this method is that this can be stored just as a set of vertices, but there's a very clever way to store it with very, very few bytes, or bits to be precise. And here's the idea for the overview idea how this works. So what is stored is not the geometry itself, but it's a path to recreate the geometry. What you see in blue here is exactly the path to recreate that geometry. Okay, so because what's an interesting insight is that when you start here, you start at some arbitrary point. Let's start here. So I just pick a random point somewhere in my mesh and I start here. Okay, and let's say I want to go this way. So from this, starting from here, there's really only one way I can do it. I can turn left. Okay, here I turn left, here I also turn left, but notice now I turn right. If I would have turned left one more time, I would have made it all the way. Okay, so, but by turning right, I say, okay, well, if I turn right, then this means the next edge is to the right. It's not to the left. And then go left again, and then right, and so on and so forth. So if you think about this for a while, I don't want to go into the details. If you're interested about the details, I can point you to the publication. But the only thing that I want to get across here is that this entire geometry, if it's a restricted quadri, can be represented by just a series of left and right turns. Okay, so what's the left and right turn? Well, it's just one bit of information. Okay, so that said, starting at some point, we can represent every triangle, at least the topology of every triangle. So that's where are the vertices located in X and Y. That says nothing about their Z coordinate. More on that in a second. But the topology, okay, how is this set up, can be represented by 1 bit per triangle, which is extremely little information. Well, it's probably the minimum amount of information that you can imagine. Okay, that will create this crazy path here. And then you can unwind this crazy path by a bunch of rules to recreate the triangles again. Okay, so that said, we can store a sequence of bits, whereas each bit corresponds to 1 triangle. The only thing you need on top of that one is the vertex position of the triangle. How many vertices do we need per triangle? This is also an interesting insight. If I start with 1 triangle, again, say that one here, okay, and I store the first 2 vertices just verbatim, so I'll just draw them as they are. So how many more vertices do I need? Well, I need 1, then I got the whole triangle. Now, if I move to the next one, how much do I need? Well, I got this one here already from that triangle. I got this one, I need 1. Now I make another step, how much do I need? I need this one here. Now I make another step, how much do I need? This one here. So again, how much do I need in terms of the Z coordinate? Only 1 floating point value. Okay, so in summary, for every triangle, we need 1 bit of information to get its X and Y coordinates, and 1 value. We could store that in floating point, but the authors decided to store it in lower precision as a delta to the previous one, because generally values don't jump around in a terrain. So you need very little precision to encode one to the next. So they just spent a few bits for this 1 piece of height information. So in the end, it's 1 bit plus a little, if I recall correctly, it's 15 bits for the rest. So 16 bits per triangle that stores the full X, Y, and Z coordinate of every vertex. Drawback of that method is it's a run length encoding scheme. That means if you want to know what's the position here, or here, or here, or here, you have to walk all the way to get to this point here. Okay. Hence, this compression is only done per tile. Okay. It's not done for the entire domain for this whatever exabyte of data. It would crunch it down significantly, but this would mean if you want to get some piece of information somewhere in the middle of your terrain, you'd have to walk through tons of data to get there. Okay, so this is only done on a per tile basis. So, but every tile shrinks significantly, and that allows you to get away with very little information. Okay, so that said, what's the next thing that we want to do? Well, there's still the image that we need on top of that. Okay, so we have the geometry compressed down to very little data. Okay, it's basically just a path to the right or a path to the left. That's easy. Now, how do we compress the images? Well, image compression is kind of it's a relatively straightforward thing, right? You're on JPEG or PNG or whatever. And they work well. So PNG is usually used for high quality or more like cartoon style things where you have flat areas. And JPEG is usually used for smooth, more photographic type of images. And I'll talk about those techniques way later in the stream. Not today, but in a later stream. I'll also talk a little bit about the details about PNG and JPEG. One of the issues with those is, though, that they aren't really well suited for processing as textures. The reason is they also use run length encoding scheme. They use compression schemes that work incrementally. So while there is some progressiveness in JPEG, still, if you want to access a certain piece of information, you have to first decode a certain area. Not like these areas are gigantic, right? They're 16 by 16 pixels, but still you have to decode parts. And at least at the time where this method was invented, there wasn't any easy access to the JPEG decoding hardware. So the authors decided to pick a technique that works transparently on a graphics card, and they decided to go for S3TC, which stands for S3 texture compression. S3 was a company that was bought by, I think it was NVIDIA. It was either ATI or NVIDIA, and ATI was later on bought by AMD. I'm not sure I think it was actually ADI. Anyways, it was a company that worked on texture compression, also developed graphics hardware, but then was bought by one of the big competitors. And the idea of S3TC is that it's something that is implemented in hardware and that happens without you even knowing about it. So you just upload a compressed texture and you access this one as if it would be a normal texture. It's just smaller, but it gives you the same access functions in the shader. It's also referred to as DXT1, which is direct access name for a similar idea. Okay, so DXT1 stands for DirectX texture compression format 1, and it's about the same idea. It's a lossy compression scheme, and the cool thing is it works on the fly in relatively small blocks, but you don't even need to worry about those blocks. So all of this is done for you. And the idea is super simple. It's actually surprising that it works at all, given that it's so simple. So here's the idea how to decode an S3TC compressed image, or in particular 4x4 block. So the image is processed block by block. So we just worry about one block, and then if we want to compress the entire thing, we would just process in a divide and conquer fashion. So this is a block of data, and that's stored as 16 times 2 bits. So extremely little data being stored. Okay, we got a question here. Let's just I would kind of flip it around. DXT1 is another name for S3TC. Because S3TC is actually the older idea, but yeah, it's the same thing. There's different subcategories. But yeah, it's the same concept. So now, so how does it work? So first of all, we store very little memory per pixel. 2 bits is not very much. Just gives us basically 4 choices. On top of that, we store another 32 bits of data, and this allows us to store 2 colors in, well, a reasonable quality. Usually you have 24 bits of color, so we'll just use 16 bits and quantize the colors a little bit more. And from these 2 colors, in this example here, red and blue, so those 2 colors here, red at the top, blue at the bottom. From those 2, I interpolate 2 other colors, just as the linear interpolation. So I basically compute 2 averages to other colors, which gives me 4 colors in total, whereas only 2 are specified and the others are computed from the 2. And I use those 2 bits to pick any of the 4 colors which fits best. Okay, so in other words, for every 4x4 block, I read 16 times 2, 32 bits, plus another 32 bits, so a total of 64 bits. I read 64 bits of data. I take the first 32 bits, blow it up into 4 colors, and then just pick for all of those one of the 4 colors. So every 4x4 block can only have 4 distinct colors at most. Now, what's the rationale behind that? Well, the rationale is a 4x4 block is a fairly small block, so the likelihood that all 4 pixels will be about the same, or at least very, very similar, is very high. Okay, so, and even if they differ significantly, where would that happen? Well, it would happen in an edge, right? So you have an edge in a line in your image, right? A black line on a white canvas. I can still store 2 colors perfectly, or at 16 bits, so I can store black and white, and then maybe a few grayscales, 2 grayscales adjacent to that, which would put you 2 interpolating colors. That's kind of the rationale behind this. What's interesting about this compression scheme is, and that's actually a thing that a lot of compression schemes have in common, only the decoding is specified. This is specified. What is completely open to you is how do you encode the data? How, given an image, how do I turn it into this thing here? You can do it any way you want, right? You can do pretty stupid about it. You can, take a 4x4 bit block, compute the average color, call all of the blocks 0, and just store that average color. Would work fine. Okay, would probably not make a very good use of the resources, but it's okay as long as you're happy with the result. So the encoding is up to you. The decoding is done by the graphics card. So you just upload these numbers, these 64 bits of data, and they represent a 4x4 block. And then in the shader, you can just write texture access and it'll do the decoding all for you transparently. So how is the encoding done? Well, there's two popular ways how to do it. One is a little bit quicker with a somewhat worse quality, and the other one's a little bit slower with a better quality. Well, kind of the opposite. The cheap one is called range fit, and the idea is also very similar to other compression methods, is that if you imagine your points, your red, green, blue pixels as points in 3D space, I ignore blue here so that I can draw it in 2D. Okay, so we now have 2D points, but of course those are 3D points with blue with the third coordinates. Okay, but the idea is the same in any dimensionality. So what we do is we first compute the principal axis. So that's the axis where this cluster of points has its maximum length. Okay, so this is trying to figure out like into what axis is this stretched. Okay, if you want to know more, you can just look up principal component analysis. So this is just the axis of maximum extent. And the next thing we do, we project every point, all of our 16 points, we project them onto the axis. Okay, and those are those little lines here. Okay, you see we compute the projection down of all of those points onto that axis. And then I figure out which are the two extremal points. So which is the first and the last. So those are the ones that I've coded here. So this is the first point. This projection is the first on the line. And this is the last one. That's this projection is the last on the line. And I simply take these 2 points as my two colors. Okay. So just pick those two. That means I interpolate the other 2 colors. They're automatically generated. And now all I do is for each of those 16 points, I simply check to which of those 4 points are they closest. Obviously, the first and last is hit perfectly. And the others, well, they shouldn't be too far away because the whole thing is stretched in that direction. Right? So that's called range fit. And it gives me both the 2 colors as well as the assignment, this 2-bit value to which of the what's called centroids these colors belong. What this optimized is, well, it optimized obviously the 2 extremal points, which is maybe not the best idea, right? Imagine that one of your points is like way off the others. And then the question is, should we waste a lot of quality just to capture that point? Because what will happen if one of the points is completely off, say this point is, I don't know, here, right? We will hit it perfectly. Next point is here. Next interpolated point is here, and then the 4th one is there, so all the other points get mapped to the 4th one. The question is whether or not that's a good idea. Well, I would say it depends, but it's probably generally not a good idea. Is this only done? Well, since the computation of the 2 colors is fixed for S3TC and it's done in RGB, you probably want to do this computation here in RGB as well, right? If you do this in another color space, you could upload different colors. I mean, there's nothing wrong with like turning your entire image into HSV, for instance, doing all this process in HSV, but then you will also get HSV values back, and then you would have to turn those into RGB later on. So this could also work on, but then you would have to kind of keep this color space computation away from S3TC. So you have to first compute the color space transformation, then do this whole thing, and then in the end reverse it. And the question is whether there's things like cyclicity issues, right? So if you have cyclic spaces such as HSV, that kind of might cause issues here, right? So it's generally done in RGB. But certainly, I mean, remember the whole thing we did with the Mosaic Maker, where we also ended up using YUP as a color space to overrepresent, to on purpose overrepresent the contrast. You can do the same here, okay, if you want to. You just need to be very cautious about what's going on, because again, also the 3 components are later turned down into 16-bit, and they're non-uniformly turned into 16-bit. So there's a few more things going on here that you need to pay attention to. Okay, so that's range fit. Okay, so the other thing that's a little bit better is what's called cluster fit. It's a similar idea, but it tries to kind of optimize optimize in a more global fashion. Okay, so the first thing is the same. Again, we compute the principal axis. It's the same idea. We project the points onto the principal axis. Again, same thing. But now we iterate over all potential clusterings. What does this mean? Like, isn't that an infinite amount? No, we iterate over all clusterings that preserve, all clusters that preserve the ordering. So what does this mean? Well, we cluster those 16 points into 4 clusters. Okay, and there's only a limited number of clusters that you can choose when you want to preserve the order. So the first point into the first, none to the second, none into the third, all the others into the fourth. That's one example. Okay, the first 2 points into the first, and so on and so forth. So you basically choose along that line, you choose cut planes. You choose 3 cut planes, okay, to chop this up. So that's effectively what all of those cluster preserving orderings do. And those aren't incredibly many. Those are roughly 4K. So you iterate over those 4K clusters, and you simply do the following. So for one clusters that I happen to draw here, so I said it's just 3 cut planes. So that creates this as first cluster, this as second cluster, third cluster, and so on. Okay. Now, what we do is, for each of those clusters that I've randomly chosen, which is okay because I iterate over all of them, for each of those clusters, I find the best centroid, which for this situation, for instance, is here. Okay. So I find my centroids, and for each of those clusterings, I find the centroid for the first and the last cluster. How is this done? Well, I, for instance, compute the center of all of the points in that cluster. And from those 2 points, I interpolate the other 2 points. I can't choose them at random, right? Because they're always computed as the interpolants. But what I can do is, and by doing it this way, I can choose those 2 colors optimal for that clustering. Okay. Now what I do is I take the next arbitrary clustering, and again I choose the colors, and I iterate over all those 4,000 clusters, and in the end just pick the one that reduces the amount of error that I make, the sum of the distances, or the square of the sum of the distances. Okay? So generally use a squared distance. And then you pick the one that is best. What does this mean? C1 doesn't look like it's the center of the cluster. It does not look like it's the center of the cluster. Yeah, you're right. So it doesn't look much like the center of the cluster, but it looks like it's the value that minimizes the error here when I choose this one, and I get the corresponding points for this one and this one. Then this point here minimizes the distance to all of the centroids from all of the clusters. Okay, so moving, so maybe I explained this a little bit incorrectly, or at least it was. So this one is chosen that it's the center, or that its position leads to these positions here, which in essence are all on the minimum distance to all of the points in their corresponding clusters. Okay, so that makes a lot more sense. Does that make sense? Okay. For that, it's not necessarily the center of that cluster itself, but it leads to an overall centering of all the clusters. Okay, does that make sense? I guess yes. Okay, so got it. Okay, cool. So with that, I have to do a lot more work, about roughly 4,000 times more work, but it's still just a constant amount of time per block. So it's a constant overhead, and this often pays off to do this cluster fit. So if you just download a pre-computed, if you download an S3TC pre-computed, pre-compressed, that's it, pre-compressed texture, it's usually compressed by the means of cluster fit. Okay, so it's usually worth paying that extra amount of work. So with that one, here are a few examples. So what I find very interesting is that the overall idea is that simple, right? In particular, the decompression idea is simple, which is necessary to put it into very few transistors, very little silicon, which makes it fast. If you have small die area, you can parallelize hardware, and that makes it fast. So it sounds like it's a pretty dumb idea. At least that's what I thought when I heard about this first time, but it works pretty well. So here's an uncompressed and a compressed version, and well, it's really hard to spot a difference. Here's again, for the target aerial photographs, an uncompressed and compressed version, and well, they look pretty much indistinguishable to me. Let's zoom in into the small area, and even if we zoom in, they still look pretty indistinguishable. You can, though, tell the difference, okay, if you know what exactly to look for. So what you have to look for are, well, nearby regions, and look at the number of different colors in a nearby region. So that's how you can spot the compression. So if you look at this part of the roof here, for instance, right? And if you look at the part of the roof on the left, or here, this is probably also a roof, or it's maybe a truck. I can't really tell. But see that there's, generally colors become more uniform, which is clear because you only have 4 colors per tile. But there isn't that much fidelity in the original tiles, right? I mean, here, for instance, green is gone, right? You can probably spot this. Like here's the green is gone in that tile, right? Whereas it was present here, right? So there's green here, it's not here, but it's not a huge difference, right? So it works surprisingly well. The reason it works so well is because it works on relatively small areas, and it only gives you the relatively small compression ratio compared to things such as JPEG or PNG. But still, it's a pretty decent compression ratio without any loss in performance or functionality. And that's a really great thing because there are a couple of things you need for a terrain. So one thing, for instance, you need is to do high quality terrain rendering, you want anisotropic filtering. And that's also something that I mentioned in computer graphics already. More details on that later on in the lecture here as well. But just as a kind of a quick look ahead, if you use MIP maps, they avoid aliasing artifacts. So with increasing distance, your image becomes smoother and smoother. So you use lower resolution version of the data. It's smoother and smoother, but in particular for terrains where you look pretty tangential to a surface, you do one thing that is kind of nasty here, and that is you sample significantly different in X and in Y. What do I mean? Well, look at this red area here at the top, which I've enlarged here. So this is just a, well, pretty much square-shaped area on the screen. And what you'll notice is that you get these stripes, right? So the terrain is kind of stripy in X direction. And why is that the case? Because we've chosen a low resolution version, but we have a lot, like if you look at the pixels on screen, like this pixel here, and this pixel here, and this pixel here, how far are they away in texture coordinates? They aren't really very far away in textures. But this pixel here compared to that one, so in Y direction, they are pretty far because, well, they make a giant leap towards the back, all right? So what we do is we sample with different sampling rates in X and in Y. And if we rotate the camera, this sampling pattern changes. So if we choose a downsampled version, it's okay maybe in Y, but it's too downsampled in X. And this is why we see these stripes, because we see smoothing going on here. And for that, you need different versions in pretty much any direction. Okay, and that's what's called anisotropic filtering. If you do this to the texture here, you recover a lot of the quality. But to do this, you need to have some sort of compression that kind of works together with all of those concepts such as MIP maps or anisotropic filtering. And S3TC has this great advantage that it's nicely integrated into the entire pipeline, or DXT1, as well as the other DXTs. Okay, so this is what makes S3TC such a nice choice. Now, if you combine all that together, the compression of the geometry, the compression of the texture, the tiling of the geometry and the texture, and just processing one tile after the other, you can render very high resolution terrains that meet geometry as well as aerial photographs at pretty decent resolution. So here are some timings on an arbitrary system. It's actually a pretty slow system. Okay, so let me get out of the way. Okay, so this here is Utah, that's the Utah Valley. It's a decent resolution, so it's 1 meter texture resolution, so 1 meter per pixel. And also the height field is pretty decent, so about every 5 meters we have a sample point. The area covered, the Rocky Mountains here, as well as the Salt Lake Valley, are about roughly 500 times 500 kilometers. it's roughly a terabyte in data. And when you pre-process it the way that I just described, you need about 2 million triangles to render this. So this, what you see here, is made up of roughly 2 million triangles. Okay, so how do I come up with a number? Well, it turns out that for this type of terrain, so being flat in some areas, being curved in other areas, a given resolution, I think it's 1080p, full HD resolution, you need about 2 million triangles. Given the hardware that we run this on, which is, I guess, well, it's probably today, it's I guess, cell phone level hardware these days. So you can render this at roughly 200 frames per second. So about 400 triangles per second can be processed by this hardware. Like the shading itself doesn't cost anything, right? We just map a texture on it, so that's super cheap. So it's usually dominated by the number of triangles. Okay, and what's going on under the hood? Okay, so all I talked about is the data pre-processing, right? And code this as a path and then compress the texture. But how's this stuff rendered? Okay, so it's rendered with the rasterizer. So it's rendered with the OpenGL or DirectX straightforward sort of rasterizer, just doing this thing tile by tile. And just as a kind of refresher, how does the rasterizer work? Well, it's a technique that works from the object. Okay, so it processes one triangle after the other, and all those triangles are then projected onto the screen, so the coverage is computed, it's rasterized. So that's how a rasterizer works, kind of in a nutshell. Okay, if you want to know more, well, I did this very extensive review of OpenGL at the beginning of this term. So, and again, we just need to be, we can be very rough here. So how long does this take approximately, like in terms of O notation? Okay, so let's look at this. Well, it takes some time, and the time to do this is basically how long does it take to process a triangle, and how long does it take to process a fragment? Okay, so we basically, if we know the number of triangles that are generated or that are necessary, we know the number of fragments that are generated, we can compute the time one is executed after the other. So let's forget about the fact that it's a pipeline. So let's just say it all uses the same hardware, which it does these days with unified shaders. So the overall time is just O of t, so the time it takes to process all the triangles, plus O of f, the time it takes to process all the fragments. Okay, and whatever this time is, it's something that's linear, twice as many triangles, twice the time. So in other words, what this means in total is that we have some constant that is dependent on your graphics hardware or your overall system, times the number of triangles plus some other constant, times the number of fragments plus some overhead that your graphics card needs to start a frame. Okay, so in total you get this C1, constant 1, times T plus C2 times F plus D3. So that's the time it takes to render a frame. Very general, right? So there's hardly anything to say against this. So, good, it's all cool, and apparently that is fast enough. I mean, 200 frames is fine. So now let's look at another data set here. Okay, so this here is another data set. It's just a different part of the world. It's Vorarlberg in Austria. It's a different data set, and the big difference is, compared to the Utah data set, is not so much the landscape, right? I mean, obviously Utah is pretty dry, but other than that, it's also got big mountains. It's not the Rocky Mountains, the Alps here, but overall, same idea, flat mountains. What happens is, though, even though the data set is roughly the same size, right? It's 800 gigabytes, so it's a little bit less than a terabyte here. Same size. It has significantly higher spatial resolution. Okay, so the texture, for this data set, it's very high resolution. So it's one sample point every about 12 centimeters. And the height field is also significantly higher. It's about one sample point per meter. So consequently, the area is much smaller, 56 by 85 kilometers, but the data size is the same. Interestingly, what this leads to is, when we kind of play around here, look at the data. If we have a higher resolution, what we suddenly get is we have, well, obviously more detail. And you see that at that resolution level, your trees are samples, not just the trees. At 1 meter resolution, you actually get cows. You get power lines, you get sheep, you get cars. They end up creating geometry. Okay? So, and what that leads to is a significantly higher number of triangles that you need per frame. So, to render this image here, we need about 30 million triangles per frame, which for the same piece of hardware that can render roughly these 400 triangles per frame, you end up with just 14 frames per second. So why is this suddenly slower? I mean, it's the same amount of data, and we use this multi-resolution structure. We reduce the resolution in flat regions, we increase the resolution with distance, right? So we pick lower resolution tiles when we get further away, similar to Rome, except that we only pick the tiles. We don't reduce the triangles in the tiles. But we still suddenly need more triangles. Well, the reason is simple. What happened for the Utah data set is that we ran out of resolution. So for the nearby parts of the data set, we could have rendered that at higher resolution, but we just didn't have the resolution. Okay, so we just ran out of data. So when you do a multi-resolution approach, right, you use low resolution at the back, and then you increase it up to the point where you don't have more data. And then even if it gets closer, well, you can increase the resolution. You stick with the low resolution version. Okay, so but if you have super high resolution, this point at which you can't increase it any further moves toward the front, and you totally need more. So that's one. Act two is, as it turned out, for terrains, if you have higher resolution, well, you also want that. Okay, here's that data set in filled mode and the restricted quad tree as a wireframe. And as you can see, there's still planes, right? There's still planar regions. But since you have so many points, a lot of error would accumulate if you remove them. I mean, there's other regions in the data set here where you have gravel, and since you'd sample this at 1 meter and texture resolution is even higher, you actually get a pretty good approximation of the gravel. So it turns out that for high resolution data sets, there aren't really any super flat regions. So the static simplification, while it still works, right? I mean, see that there's lower resolution regions here at the back. So the static doesn't help you that much anymore, unless you kind of increase your error rate, but that would effectively get rid of all your nice high resolution data. So bottom line is, we've reached a point where the data is so high that we're too slow. So our raycasting idea, this time per triangle plus time per fragment, is too long. And in particular, the time per triangle is the deal. Okay, so if I increase the resolution, if I do more triangles, it's not like I have to render more fragments. I render more triangles. So time per triangle apparently takes too long. Okay? So what can we do? Well, we can stick with the same data structures and all. We just swap out the rendering approach. We go to raycasting or ray tracing. It's raycasting, ray tracing, kind of the same idea. It's just that for raycasting, we just cast one ray and don't worry about reflection rays because we have the texture already that gives us all the reflection and shadows and everything. So just again, as a refresher, how does a ray tracer or raycaster work? Well, we don't start with the geometry. We start with the pixels on screen. Okay, we start with the pixels on screen. For each pixel, we shoot one ray into the scene and we check what does it hit. Okay, and then we continue this process for the next pixel and for the next one, and we do this until we've covered all of the pixels on screen. So what is the time it takes for a raycaster to spit out an image? Well, it depends obviously on the number of pixels, and it depends on the number of what I call S here, the number of steps. So how much work do we need to do per ray? Okay, so the number of rays times the work per ray. Okay, so we get this O of P times S. Okay, and that in turn is just expressed in arithmetic, right? This is C, some constant, times P times S plus some overhead. Okay, and good. Now we observe that these two systems have different characteristics. You could argue that S depends on the number of triangles, so the steps, the computing steps I have to do per ray probably depends on the number of triangles. So somehow triangles also factors in, but it factors in differently. That's very interesting. Okay, so what else can we do? Well, we got our quad tree data structure. In particular, for a ray tracer, we can store a little bit of additional information. So for instance, for each of the tiles, we can store a box around the tile. And that box is actually pretty easy. We just store the maximum and minimum height. Okay, with just two pieces of information, we can generate the entire box if it's an axis aligned box, right? I mean, we know how big a tile is in X and in Y, so all we need is its maximum minimum height, then we got the box. Okay, and for the raycaster, to find an intersection for ray with a triangle, we first check these boxes and then we go into the triangles. That would be one approach. Of course, we can turn this into a hierarchy as well. Yeah? But that's kind of the overall idea. So we can easily compute, that's the key point, easily with very little overhead, both in times as well as in storage, compute an acceleration structure to efficiently intersect the rays with the triangles. Okay, so let's look what that looks like. So here's, again, this 4 Albert terrain, it's just a different view. And what you see here, those are those boxes. Okay, well, it's probably kind of hard to spot. That's always an issue with rendering boxes, but you can maybe for this box here tell that it belongs to that region, right? So what the raycaster does for each array, it traverses these boxes, and we can do this also very efficiently by traversing the boxes from front to back, so which it turns into a rasterization problem. It's funny that the raycaster, if you look at the implementation, becomes a rasterizer because you rasterize the ray on top of the triangle, which is following it. So effectively, those are both rasterizer really, but the idea is raycasting. Okay, but never mind the technical details here. Nonetheless, if we do this raycasting process, we can efficiently test against the boxes by rasterizing lines and then find the intersection. If we do this for the same piece of hardware that we've just used, the 420 lines, 420 million triangles per second piece of hardware, we can render this terrain here at 40 Hertz using the same compressed data structure and everything, just doing clever shaders, okay? I admit it's a huge engineering endeavor to implement this, but it can be done, gives you about 40 frames per second. Compare that to the 14 from before, and you get a significant speed up. Okay, so it's cool. I colored it in yellow here because what we want is really 60 Hertz. 60 frames per second is usually okay. So how can we do better? For that, let's compare our two approaches here. Okay, the first, the rasterizer, and the second, the ray tracer, and let's look at their performance behavior. Okay, so what's curious about these two things is that they're different. I mean, even though they render the same thing, the time it takes depends on both the fragments and the triangles, yes, but in a very different fashion. Now let's simplify these equations a little bit. For the rasterizer, it's pretty fair to say that the fragments don't really impact. Why? Because, well, first of all, it is a pipeline. All right, so the hardware is a pipeline, so a bunch of computations can be hidden. And admittedly, there's really nothing we need to do for the fragments except one texture lookup, so it's very, very cheap. So if you just basically run if you rasterize the triangles and kill all the fragments, or you rasterize the triangles and write the fragments, you end up with roughly the same performance. So we can just skip that as an approximation. For the raycaster, it turns out that these numbers of steps is pretty much a constant. Why? Because we always kind of run over the same amount of bricks over these red boxes, and that's pretty much a constant. It might be a big constant, but nonetheless, it's pretty much a constant that depends mainly on your screen resolution, but not so much on the number of triangles. Why? Because first of all, well, we don't check each triangle first, we check the boxes first, and they encapsulate a ton of triangles. So again, we can encode this number of steps into the constant. Maybe we say, okay, it takes 10 times longer. Okay, so we get another constant that I call C4 prime here instead of C4. But bottom line is, it's also a pretty decent approximation to say this thing depends on the number of pixels and the other one depends on the number of triangles. And that's now very because these two things are entirely independent. Okay, so if we do this computation, you can repeat this for pretty much any part of the terrain. Remember, we want to process this terrain tile by tile. We want to be able to load a tile, render it, or render whatever its footprint is, throw it away, and do the next one. Okay, and we either want to raycast it or rasterize it. Now, what we see here is that for tiles that are made up of a ton of triangles, the first one will be slow, and the second one doesn't care. For tiles that have a significant footprint that are very big on the screen, the raycaster is probably going to be slow because it impacts a ton of fragments, but the rasterizer, if it doesn't have so many triangles, doesn't care because its it's independent of the number of fragments. What this amounts to is that, well, if we do a hybrid approach where we, for each tile, decide whether we want to rasterize it or raycast it, we can probably achieve something better. And that's what you see here. So here is again for Alberg with two different types of colored boxes, green ones and red ones. The green ones are rasterized, the red ones are ray traced. Okay, here's another screenshot. And what you can see is, notice that there's red boxes where the trees are. Okay, this is where a lot of geometries happen. There's more green ones where, well, there aren't so many trees. Also, going back to this image, at the front we have a few green ones. Those are big. At the back we have maybe more red ones. So, how will we figure that out? Well, what do we know about each tile? Well, we certainly know its amount of triangles. Okay, so this is something that we can store per tile. Okay, so when we load one tile from disk, we can just look at how many triangles did we just load, how many triangles are in this tile. What we can also do is figure out how big is a tile on screen. We can just do an approximation here. We can take the bounding box and check the distance to the bounding box, and from the shape of the bounding box, we can do a pretty decent approximation. How many fragments on screen will that produce? Okay, and then if we know all those constants, C1, C2, C3, C4 prime, and so on and so forth, and those are things we can time for each piece of hardware in a quick pre-processing step before, say, the engine or the game runs, we can, for each tile, approximately compute how long will it take in seconds, and just pick the approach that's quicker. And we just need to switch between two rendering approaches, which turns out to be just switching out a set of shaders. So this can be done literally thousands of times when the frame is rendered. And with that same hardware, we can render 4Albert at 65 Hertz, which is above our 60 Hertz threshold. Okay, so how does that look? Well, here is how this looks as an animated scene. I've shown that at the beginning of this lecture, and as you can see, since it's decided per frame and per brick, you see how colors change when I fly over this. All right, so when bricks become bigger on screen, the system might switch to a rasterizer, for example, or if an existing brick is reduced in size because it now is closer to the camera, it might have significantly more triangle, so the system switches to a raycaster. And in summary, that gives you very high performance with a very well controllable error ratio, because we can, for each brick, decide, okay, do we want to subsample that? Do we want to use a higher or lower resolution so we don't end up with a flat horizon? We can still use whatever resolution is necessary to preserve that, while achieving very high quality and very high performance at the same point. Implementing this thing is a nightmare, okay, to say the least, because you got literally tens of, well, dozens of shaders, let's put it like this, dozens of shaders that do various processes in the pipeline, like decode this stuff, decode these runs, do the raycasting, do the rasterization, create the geometry in a geometry shader, create these bounding boxes, and so on. So it's a pain to implement. Well, once you implement this, it's an extremely high resolution, high quality, and high performance rendering system. As far as I know, it's still the fastest one in existence. Okay, so that is GPU-friendly terrain rendering, and that's it for terrain rendering. So the next topic will be terrain synthesis, which is something that I want to start on Thursday. And so far, we have a few minutes left, so roughly 15 minutes. So, any question? We got one. How to handle the texture sampling for both methods in a unique way, especially anisotropic filtering? Well, that's a good question. Thing is, you don't care, because all you do is, well, once you figure out whether once you for a pixel. You figure out what to draw that pixel. Okay, for a raycaster, you compute the position, you compute the texture coordinate, and then, well, you do texture fetch. And you let the texturing hardware do the rest for you. Okay, so for a rasterizer, you take your triangle, you rasterize it on screen, you compute the texture coordinate, you do your texture fetch, and you let the texture hardware do the rest for you. Of course, if you know a few details about anisotropic filtering, there's certain deltas that are necessary, right? You need to know the deltas, the sampling deltas. But all of those can be computed in pretty much the same way, both for the rasterizer as well as the raycaster, because all you do at the end, once you've figured out the geometry, is you apply a texture to a point where you know its texture coordinates. Okay, technically you could even do this as a deferred shading step. Okay, so you could just compute the geometry first and just write the positions out, and then have a second pass that just takes that position map, this 2D position map, and textures it. And in that case, you would see no difference at all. So the second pass wouldn't even care how the first parts generated the geometry. So actually that is the easy part. What's the not so easy part is how do we deal with the geometry? Okay, and here's the thing. For the rasterizer, when you use this path compressed geometry, what the implementation does is it takes that geometry, runs it through a geometry shader, and decodes this run, uses the delta in height, and generates a, say, 512 by 512 multi-resolution restricted quad tree triangle mesh. Now, the raycaster doesn't like the triangle mesh. Okay, what the raycaster prefers is otherwise it would have to compute ray triangle intersections, which we want to avoid. We want to do steps. What the raycaster in turn prefers is the original version. It works much better, much faster on the height field, on the regular height field, right? Just X, Y, Z values. Because what you can then do to find the intersection, I said the raycaster is really just another rasterizer. What you do is you just simply rasterize the line on top of the terrain, and for each rasterized pixel, you check its downward projection, whether it changed from above to below the terrain at that point. Okay, so that gives you the intersection point. So, and then if you have a bounding box hierarchy, you can do this extremely fast. I think if I recall correctly, for a 512 by 512, on average, less than 10 checks are necessary to find the intersection. For the rasterizer, you need the data before it was turned into triangles. Now, since it's all compressed into triangles, how would you turn it back? And the way this implementation does it is by a little trick. So it takes the triangles, the compressed triangles, turns this into the uncompressed triangles on the graphics card. So the compressed data is uploaded, and the graphics card creates the uncompressed version. And for the rasterizer, it simply rendered this once seen from the top with color as height. So it basically takes this triangle mesh and converts it back into a height field, and then feeds this to the rasterizer. Okay, so this creates a little bit of an overhead, which is, by the way, captured by this constant C5. So that's the conversion overhead that needs to be taken into account. But bottom line is it's still very fast. Would the hybrid approach add complexity if adding dynamic lighting or post effects? Well, as I said, it adds complexity to a lot of things. It depends what you want to do, what exactly you want to do. The cool thing about terrains with photographs is that you get all the global illumination for free. Okay, nature does it for you. So anything like shadows, reflection, refraction, I don't know, crazy albedo things, it's all in the photograph, right? So if you have an actual terrain and you have an orthographic photo, there's really nothing you need to do, unless you want to change lighting conditions. Okay, so if you're fine with just the way it is, it's actually, as I said, nature does it for you. So nature does it pretty well in parallel and does it in real time. So that's really fascinating. But nonetheless, if you want to do something else, which you will later see, for instance, for terrains, if you generate terrains, if you not happen to fly to a different a galaxy and photograph a planet, so you want to still recreate that, you might have to compute lighting. And there's two ways how to approach this. One is to pre-compute everything. To simply take the terrain once and then in a painstakingly slow process compute the photo. okay? And you can do all the fancy things that you want, like reflections, refractions, albedos, whatever, and just go with that. And that's probably the easiest way because well, it doesn't add any complexity. Now, say you don't want to do that because your terrain is dynamic, right? It might change while the game or whatever runs, and your lighting is dynamic. Your sun changes, your planets, whatever, or your suns. I mean, usually you have 10 suns. Anyways, if that's the case, well, then you need to consider secondary effects in some way or another. And for that, you have to either use some of the ideas that we've presented before, right? Cube maps, environment maps, some of those ideas. And in the end, all they require is rendering the scene, right? What's the cube map? I mean, it's the scene from 6 positions. So you can run that approach that I just said, this hybrid approach, also to render cube maps, for instance. Okay. But it's probably going to take a while, right? I mean, if you're barely making the 60 hertz and you need to render 6 views, you're at 10 hertz, which is probably going to be an issue. So you need to be careful what you do here. Maybe use low resolution versions or whatever. Or you would say, well, let's pre-compute some pieces of information, just like we did for pre-computed radiance transfer. So you basically, instead of just storing an image texture, you store, for instance, radiance transfer coefficients on the terrain. So the bottom line, I guess, what it breaks down to is you need to know what you want and then try to check how much can I pre-compute. And pre-computation doesn't necessarily mean it takes hours. Maybe it just takes a second or so, which you can do over 100 frames. So you just take 100 of your frame budget, do a little bit of pre-processing, and then you can use it later on. Okay, so figure out what exactly you want as a secondary dynamic lighting effect, and then add it to it. Right? I mean, shadows are easy, for instance. Right? But other things, use a shadow map. Right? For shadows, use a shadow map. It just requires a depth map from the light source. So it depends. Long story short, highly depends. Okay. Anything else? So, is the hybrid approach also applicable for complex we call them meshes only? Well, technically, yes. I guess it didn't. Those performance metrics, right? Those C's, they might be different, right? I mean, one of the cool things about the terrain raycasting, why it's competitive, which is interesting, right? So, what I've done here is I use rasterization hardware to do something else. In this case, raycasting, right? By this idea of rasterizing a line, which effectively is raycasting. And that breaks down for other types of geometry, right? If you have general geometry, you have to come up with another clever idea to make a hardware A that's optimized for A, do a thing B, and still be competitive in performance, right? I mean, these pieces of hardware are optimized for rasterization, okay? So if you can come up with an idea to do this efficiently, yes, it might work. I mean, there's other approaches that use hybrid things. So for instance, shadows, right? You can do a shadow map with rasterization-based approaches, and then where you have, for instance, where you have transitions from shadow to light, you would do raycasting on those small regions, and that is also adaptive in that sense, right? So yeah, hybrid approaches are, you can use them for a couple of things. I mean, with the recent cards, there are some ray tracing functionalities, right? So there's some ray tracing units on the card that can also be utilized for certain regions. So in a sense, you also have hybrid computations. But the big difference is here, the hybrid computation to actually speed the thing up, right? If you use ray tracing in computer games these days with like NVIDIA's or AMD's latest technology, it usually means it costs a lot of performance, but improves the quality. So you can do a few nicer effects, or in particular, you can do the effects easier for the programming studios. Most of those effects can actually be done with clever hacks as well, but they are way easier to do. So you trade performance for quality, and you need these dedicated hardware for that. Here, it's all about performance. That's the big difference. But hybrid approaches are certainly a good idea as long as you analyze the situation properly. And as long as you have a skilled master and then PhD student who's willing to spend a few years of his life implementing this thing. Yeah, anything else? Okay, doesn't seem to be the case. Then that's it for today. Again, on Thursday, 45 minutes on terrain synthesis. How do we generate these terrains out of thin air and still get something that looks reasonable for a game, for a virtual environment, or for whatever. So that's basically what the next stream will be about. Until then, stay healthy. If you can, get your vaccination. Bye-bye and see you.